Let's start by looking at the parent exponential graphs. This is a picture that I've already shown in one of my earlier videos. So whenever you have an exponential graph, there are a couple of things that you need to immediately identify. What is the y-intercept? Is the slope of the graph positive or negative? What happens to the value of y as the value of x becomes very large? This is basically the end behavior. So the graph will either look like this, which is an increasing function, which is called growth, or it will look like a decreasing function, which is basically the decay. So how can we tell whether the slope of the graph is positive or negative? Let's say we have this equation, the simplest exponential equation, y equals b raised to power x. This base basically tells us whether the graph will be an increasing function or a decreasing function. If b is greater than 1, the slope will be positive, like in this scenario. The base is 2, so you can see the slope at every point is positive. However, if b is a fraction, b is greater than 0 and less than 1, the slope will be negative. Like in this scenario, b is a fraction, b is 0.5. So this is the first thing that you need to identify. Then we have the y-intercept. This is very important because this is the reference point of these graphs. Let's replace x with 0. What do you get? You will get y equals 1 and not y equals 0. You replace x with 0 here. What do you get? Y equals 1. So for both the graphs, the reference point will be 0, 1 and not 0, 0. Very important. Then the next point that you need to identify is, on one side, the graph will always approach infinity. Like on one side, the graph will approach infinity, and on the other side, the graph will approach the asymptote line. What is the asymptote? I've talked about this earlier. It's a line that the curve reaches as it heads towards infinity, but it will never touch this line. Very important. You see, so if we look at this graph, on the positive side, the graph is approaching infinity, and on the negative side, the graph is approaching the asymptote. If you look at this graph, what is happening here? It is approaching infinity on the negative side, and it is approaching the asymptote line on the positive side of axis. So this is something that you need to remember. And from this, you can also identify the domain and the range. So if you look at this graph, you can see the graph satisfies all values of x. Hence, the domain is x belongs to all real numbers. But the range is y is greater than 0. The graph will always be above the x-axis. Similarly, even in this graph, the domain is x belongs to all real numbers and y is greater than 0. So these are some of the things that you need to immediately identify. Now let's have a look how these graphs function when we add or subtract values into the values of x or y. So the first scenario is changing the base of the graph. Let's say we have our equation y equals b raised to power x. What happens when we change the base? So this is our parent graph, the red one, y equals 2 raised to power x, and the blue one as well, which is basically the decay, y equals 0.5 raised to power x. So if the base keeps increasing, let's say the base is 2, 3, 4 or 5, like I have in this scenario, the slope will keep increasing. Slope keeps increasing. That is what you need to understand. So see, the 5x graph has a higher slope than the 2 raised to power x graph. Similarly, if this fraction keeps increasing, the slope will keep increasing as long as it is between 0 and 1. That's something you need to understand. The next thing that you need to understand, I hope this was pretty easy. You just increase the base, the slope will increase. Either on this side or on this side, it doesn't matter. The next scenario is this one, that is reflection about the x-axis or about the y-axis. So when you have a reflection about the x-axis, the y basically becomes negative. The situation becomes like this, minus y equals 2 raised to power x. Remember the rules of reflection? We have talked about this earlier. So the equation will become like this, y equals minus 2 raised to power x. That's a reflection across the x-axis. So this is our parent graph. You reflect it across the x-axis and the graph will look something like this. So if you look at this graph, it reflects the parent graph about the x-axis. I've already talked about this. Has a y-intercept of 0, -1 now. Because it's a reflection, earlier the y-intercept was 0, 1. Now the y-intercept should be 0, -1. Has a range of, now the range is y is less than 0. The range of this graph was y is greater than 0. I think these are pretty easy things that you can definitely identify from the graph. The domain remains the same for both the graphs, that is x belongs to all real numbers here and here as well. X belongs to all real numbers. This thing doesn't change. The horizontal asymptote also doesn't change, that is at the x-axis or y equals 0. But when you have a reflection about the y-axis, you know the x basically becomes negative. So you see, this is our parent graph, this is the reflected graph, the x basically becomes negative. In this scenario, nothing basically changes. There's only reflection about the y-axis. After that, the y-intercept also remains the same. The range is also x belongs to all real numbers. The domain is x belongs to all real numbers. The range is also the same, that is y is greater than 0. But you should be familiar with these reflections. You should immediately identify that this is a reflection about the y-axis and this is a reflection about the x-axis. The next scenario is to see how the graph basically behaves when we have a vertical shift. And when does that happen? When you add or subtract a constant into the function, that is when we have a vertical shift. I've drawn 3 graphs for you. This is our parent graph, y equals 2 raised to power x, because this is the standard. We need this graph every time. This is basically, this graph is f of x plus z. So when you add a constant, the graph basically moves z units upwards. And this graph is basically f of x minus z. When you subtract a constant from the function, the graph moves z units downwards. So let's have a look at the characteristics of each graph. The domain basically remains unchanged. When you have a vertical shift, x belongs to all real numbers is your domain. All values of x will satisfy all these graphs. Whenever you have a vertical shift, please remember this. So when the function is shifted up 3 units, like in this scenario, let's discuss g of x first. We have 2 raised to power x plus 3. The y-intercept shifts up 3 units. So when you shift 3 units up, the y-intercept will become 0, 4. Please remember, this does not mean that the y-intercept is 3. So if you replace x with 0, you will get 1 plus 3. So that will result in 4. Remember, our reference point is 0, 1 and not 0, 0. So please remember that. The asymptote also shifts up 3 units. So the asymptote will now be y equals 3. This graph will approach this line but will never touch this line. That is the reason the range becomes y is greater than 0. Now let's have a look at the second graph, which is basically 2 raised to power x minus 3. I've called it h of x. This graph that I'm talking about. Okay. The y-intercept shifts down 3 units. Earlier it was shifting up. Now it is shifting down 3 units and it will result in this point 0, minus 2. The asymptote similarly will also shift down 3 units to y equals minus 3. Now the asymptote is this line. The graph will reach this line as it heads towards infinity but will never touch this line. I've talked about this earlier multiple times. The range is y is greater than minus 3. The asymptote basically gives you your range. Above or below that line will be our range. Please remember this thing. The next scenario is obviously the horizontal shift. And when does that happen? When we add or subtract a constant into the value of x, we have horizontal shifts. We have talked about this multiple times before. But this time the shift is basically opposite. When you add a constant into the value of x, the graph basically moves z units to the left. And when you subtract a constant, let me use a different color. When you subtract a constant from the value of x, the graph basically moves z units to the right. Let's have a look at our various graphs. So this one is our parent graph, y equals 2 raised to power x. What will happen if we have y equals 2 raised to power x plus 3? Now we have added 3 units to the value of x. Just pick up this graph and move it 3 units to the left, and we will have this graph. So you see, the domain will always remain unchanged. Let me first talk about this graph as well. So what happens if we subtract 3 units from the value of x? We will have 2 raised to power x minus 3. You just pick up this graph and move it 3 units to the right. The graphs will look like this. Now let's look at these important points. The domain definitely remains unchanged. It will satisfy all values of x, so x belongs to all real numbers. The asymptote also remains unchanged, that is y equals 0. Y-intercept is important in this scenario. Y-intercept shifts. Now in this graph, the y-intercept is 8. How did we get 8? Now you need to evaluate this function. Can I rewrite this function like this? Y equals 2 raised to power x into 2 raised to power 3. Remember the rules of exponent? So we have 8 into 2 raised to power x. Now this is in the form ab raised to power x, where a is our initial function. So this is our initial value. This is the point from where the graph basically starts. That is why y equals 8. Similarly, if you look at this equation, it will look something like this. Let's solve this as well. We have y equals 2 raised to power x into 2 raised to power minus 3, which basically becomes 1 over 8 into 2 raised to power x. So our initial point is 1 over 8. So the y-intercept is 0, 1 by 8. This is something that you need to understand. I have also written this over here so that you can pause the video and read this if you want. Let's now have a look at both the shifts together, horizontal and vertical shifts. So if you have an equation like this, which is f of x equals 2 raised to power x plus 1 minus 3. Now this basically tells us that the graph will move 1 unit to the left. You are adding a value into the value of x. And this is basically f of x minus z, that the graph will move 3 units downwards. So the graph will basically look like this. The first thing to identify is the asymptote. This constant basically tells you the asymptote. Please remember this thing. So you will draw a line at y equals minus 3. And then what will be your y-intercept? You replace x equals 0. What do you get? You will get 2 raised to power 1, 2 raised to power 1 minus 3. So that is basically minus 1. So see, the y-intercept is at 0, minus 1. So these are the things that you need to identify. So this is basically your parent graph. If I draw it over here, I will use a green color for that. Our graph basically looks like this. This is our normal graph of y equals, let's say, 2 raised to power x. So when this graph basically moves 1 unit to the left, all the points will move 1 unit to the left and then 3 units downwards. So this point will come over here and then move 3 units downwards. See, so minus 1, 0, minus 1, minus 2. This point will come over here. These are the things that you need to identify. That's it. Similarly, if we have an equation y equals 2 raised to power x minus 1 plus 3. Now what happens over here? We are subtracting a value from the value of x. That means the graph will move 1 unit to the right and 3 units upwards. So our asymptote will be at y equals 3. This is our asymptote, where this is basically the line where the curve approaches as it heads towards infinity. And then what will be the x-intercept and the y-intercepts? For y-intercept, we equate x equals 0. What do you get? You will get 2 raised to power minus 1 plus 3, which is basically 1 over 2 plus 3, that is 3.5. So have a look at this. The y-intercept is at 0, 3.5. And you won't have an x-intercept because the asymptote is at y equals 3. These are the things that you need to identify. That's it. Now that you are familiar with these graphs, let's have a look at this past paper question. F of x equals 2 raised to power x plus 1. Okay, so this is a vertical shift. This is basically f of x plus z. So our base graph is basically moving 1 unit upwards. This is something you should immediately identify. The function f is defined by the equation above. Which of the following is the graph of y equals minus f of x in the xy plane? Minus f of x is basically reflection across the x-axis. Again, something you should immediately identify, reflection across the x-axis. Now, how do I know that this is a reflection across the x-axis? Because y is getting negative. Whenever you have this, that shows that it's a reflection across the x-axis. Okay, so if it's a reflection across the x-axis, it will be a negative graph. So definitely this is not possible. This is an increasing function. No, it's not possible. We will have a decreasing function, because if this is increasing, the reflection should definitely be decreasing. This is something you should immediately identify. Now this is decreasing and this is decreasing. Now if you are a little smart, you will definitely understand that the graph of 2 raised to power x plus 1 looks like this. This is the graph of 2 raised to power x plus 1, and the y-intercept is basically 2, because it is going 1 unit upwards and our reference point is 0, 1. And if you are confused, you can solve for the y-intercept and see. If x equals 0, what do you get? You will get 2 raised to power 0 plus 1, which is basically 1 plus 1, it is 2. So once you reflect this graph, you will have this kind of a figure. The figure should look something like this, and its y-intercept should be minus 2. And C is the only graph which satisfies this equation. And again, if you get confused, you can't identify this, solve this equation. If we have minus f of x, the equation will look something like this. We have minus this function 2 raised to power x plus 1. And the function becomes minus 2 raised to power x minus 1. Put x equals 0 for the y-intercept. What do you get? You will get minus 1, which is minus 2, which is only possible in option choice C. Let's evaluate this question. An exponential function is graphed in the xy plane below. Which of the following equations could represent the graph? Let's have a look at our graph. So first thing to identify is that it's a decreasing function. It basically shows decay. That's the first hint you are getting. The second is your asymptote, which is at y equals 1 and not at y equals 0. So that's a huge hint. The function basically looks something like this, f of x plus z. And this z basically tells us our asymptote, which in this case is 1. So the equation should look something like this, f of x plus 1. With this, you can immediately eliminate option choice C and D. Now you have to look at A and B. And you know that the graph is a decreasing function, hence it can't be option choice A because the base is positive. This is the graph of growth. So we are left with option choice B. This is something that every student should be able to do. And if you are a little smart, you should immediately identify that this graph is basically a reflection of a graph, reflection across the y-axis. How do I know that it's a reflection across the y-axis? Because my x is negative. The parent graph should look something like this. The graph is this, y equals 2 raised to power x plus 1. This graph is reflected across the y-axis, and that is why your x becomes negative and we get this shape. This is something you should also be able to identify. Another interesting question. An exponential function is graphed in the xy plane below. Which of the following equations could represent the graph? Okay, so the first thing to identify is that the graph is decreasing, so it shows decay. The second thing to identify is the y-intercept, which is at 0, 2. And lastly, our asymptote is at y equals 0. It means f of x plus z, and z is 0. Okay, so we don't have any constant with these functions. That's fine. Now we need to identify these two things. The graph is going downwards and the y-intercept is at 2. So if the graph is basically decreasing, you should remember this rule. A b raised to power x is our basically function. And if the graph is decreasing, b is a fraction. B is greater than 0 and less than 1. This is something that we have already studied. Let's have a look at these option choices. So if now this is basically base, this is greater than 1, so A can't be the option choice. In B, the B is basically a fraction. Let's keep this one. Base is greater than 1, this is definitely wrong. Base is greater than 1, this is also wrong. All the option choices have been eliminated. Okay, this is interesting. So now if you replace x with 0, if I replace x with 0, what do you get? You will get 2 raised to power 0.75 raised to power 1. Yes, our intercept is also 2 and b is also a fraction between 0 and 1. Definitely your option choice is B. See, these questions are very interesting and trust me, they're easy. They're not difficult. And in most of the cases like this, like 3 options have been eliminated. So we're only left with one option choice and that has to be the correct answer.